In this video, we're going to explore another simple differential equation, just a minor tweak to what we've seen earlier, but an important change. Here, we're looking at an equation where we have the second derivative of y involved, and our goal is to solve for y as a function of x, or y as a function of t in this case here. Quick nomenclature note, this is called a second order differential equation because we have two derivatives, or a second derivative, in the equation. The earlier equations we looked at would have been first order because they only had one derivative, or the first derivative. So for a moment, try to think of two functions, or let's settle for one function, that would satisfy this equation. Take the derivative of y twice and get back to y but with a negative sign. Well, we've seen something like this before, so one guess that we might have is y equals e to the, well, not t, maybe negative t. That negative might pop out the way we want to. As with any other equation, if someone gives you a guess as to the solution, you can verify it or check it by subbing in to the left-hand side and the right-hand side and seeing if you get an equality on both sides. Well, the left-hand side is the second derivative of e to the minus t. Well, that, we can take one derivative, will give us e to the negative t with a minus sign out front. That's one derivative. Then, if we take the derivative again, we have the first minus sign, but then we get another minus sign, e to the minus t, and that ends up being positive e to the minus t. Now that's not quite what we want because the right-hand side is minus y, but we assumed y was e to the negative t. And what do we get? We get two things that are close, so close, but they are not equal. And so that means that this guess as to our solution cannot be correct. Well, thinking about our families of functions, things that we know, all the common themes, something that we differentiate twice that turns back to itself, hopefully another family that occurred to you was the family of trig functions. Let's choose sine of x to start. If we take sine of x and we plug that into our equation, the left-hand side is the second derivative of y, which is the second derivative of sine of x. Take the first derivative. When we do that, we get the derivative of sine is cos. So one derivative down, one more to go. Take the second derivative, and we get the derivative of cos is minus sine of x. Ah, hello, negative popped out. Meanwhile, the right-hand side is just negative y, but going back to the very top, that's what we defined as y, negative sine of x is what we end up in the entirety. These are equal. And so y equals sine of x is a solution. And it shouldn't come as a huge shock that if you did the same work again, we could find that cos of x, or rather cos of t, and all of this, these should all be t's, my apologies. Cos of t would satisfy the same equation. If we put cos of t, differentiate it twice, we're going to get negative cos of t, which is exactly equal to the right-hand side of negative cos of t as well. So in this scenario, we end up with two functions that satisfy the differential equation, sine and cos of t. Now, sine of t and cos of t are not the only possibilities for solutions to this equation. As with earlier examples, we should be able to maybe scale these or maybe even combine them to get other solutions. One of the ways to do that is to imagine what we did before, put a multiplier in front of the sign that would multiply both y and its derivative as a constant. And surprisingly, we can actually combine that with the same kind of scaling for the cos of t and just adding those two together. Let's do a quick check on that. The left-hand side of our equation is still the second derivative of y, which is now, we think, something a little more complicated, but fortunately not that hard to differentiate. Sine of t plus b cos of t. Differentiate it once. Take the first derivative, we're going to have a times cos minus b times sine, derivative of cos being sine, and we still have one more derivative to take. So we take our second derivative, and that gives us a times the derivative of cos is negative sine, so negative sine of t with an a multiplier, and this time the b stays the same, the negative stays the same, and the derivative of sine is cosine. Meanwhile, the right-hand side is just minus y. Well, that's minus this entire expression here. Hey, that starts to look familiar. If we imply this negative or expand this negative into the two terms here, we see that these are equal. So a family of solutions, y equals some constant times sine plus some other constant times cos, and we could pick any constants we like in here. That is a family of solutions, are all solutions, plural sense. And again, we found this a bit by guessing and checking, looking at the form of the equation, trying to identify functions that might satisfy this, but we can always show or confirm that what we found is a solution by subbing it into the left-hand side, subbing it into the right-hand side, and seeing if the two sides end up being equal in the end.